Shall we?
Yeah, I think over to you. Yeah, please begin. I think
Yeah.
Ritesh is only missing, but he's also the last speaker, the last person.
Okay.
We can also probably disable the meeting room so that people can join in without you having to admit them.
Sure.
Welcome everyone to this second session on Sun and Solar System. We have 5 talks, and the first one is by Shashikiran Ganesh at PRL on minor bodies and their composition. So Shashi, could you start sharing your slides?
Yeah, thanks. You can hear me, right?
Yes, so over to you.
Okay, thanks. Is it visible? I think. It's visible, right?
Yes, it is. Please go ahead.
Thanks. Okay, so first of all, thank you very much to the SOC for inviting me for this presentation regarding the recent results from our group here at PRL and our collaborators from other places. It's a pleasure to be present at the SI, and although it's in a virtual mode this time, but still I think it's quite exciting to see a lot of results and things coming up, and how smoothly the things are going. So what I shall be doing in the next half an hour is to give you a very brief overview about minor bodies, and in fact almost negligible overview, and come straight almost to the results that we have obtained, just focusing on 2 of the very recent papers. There have been other results in recent times, but I will not have time to go into them in more detail. So the results have been mostly the work of the Arvind and Pritish. Pritish is a postdoc at PRL, and Arvind is doing his PhD with me. And of course, we would like to acknowledge and thank the members, colleagues from IIA for their support in obtaining the telescope time on the HCT, and for their continued cooperation and support during the observing. So what are minor bodies? And so let me just go to the, So the outline is like this. I have already mentioned that I'll just give you one brief idea about minor bodies. And then, although I'm saying minor bodies here, mostly I'm focusing only on comets, and we'll see further how things progress. I'll be discussing the polarization and dust modeling and spectroscopy of various objects very briefly again, and a little more detail about the interstellar comet that we were able to observe quite astonishingly here in both at Hanle as well as from Mount Abu. And then I'll just conclude with a brief summary and overview. So the motivation for cometary observations are that these are pristine remnants from the formation of the solar system. Most of the time they are at far off distances, several tens to thousands of AU away from the sun. And they become active when they move closer to the sun. And they start to sport dust and ion tails pointing away from the sun. And as these come closer to perihelion, you can start seeing molecular emissions. Example of this you already seen is a favorite picture of mine because it was taken in the evening twilight. And comet Hale-Bopp was extremely bright at that time for those who have been fortunate enough to see it. This was a film photograph with a 2-minute exposure, so you can see the star trails also. The dust tail is curved here like this, and the ion tail is pointing away from the sun, which is just set behind the building here. That's the Mount Abu Observatory dome on the left. So typically what happens when the comet comes close to the sun, this is the example of comet Hyakutake, is that material starts sublimating, and the dust and the ions, they start to move away. Now the ions move directly away from the comet, and they follow the solar wind pattern, whereas the dust has some amount of momentum from the orbit of the comet, and that produces the curved tail. This specific comet was Comet Hyakutake, which came just before Comet Hale-Bopp. Another example is this comet Lovejoy, which was the Great Christmas Comet of 2011, W3. And in fact, it was a sun-grazing comet, which meant that it in fact dipped into the solar corona and came back. And you can see that towards the end, when it just moves out behind the sun, in fact, when it emerges, there is no tail because the tail has been completely removed by the encounter with the sun, and then it regrows somewhere at this point, just outside. Okay, so you can start seeing this tail emerging back. So this is how the comet behavior is when you consider their normal behavior. And basic things are that the basic idea is that the comets are very similar to they're pristine remnants from this time of formation. How do we say that? Again, coming to Comet Hale-Bopp, this was in fact a conjecture based on various planet formation theories. And this conjecture was more or less accepted once the similarity of Comet Hale-Bopp spectra in the infrared with the young stellar object was seen. These were among the first results where the olivine bands in the mid-infrared were spotted in Comet Hale-Bopp with the Infrared Space Observatory SWS, and very similar to the other comets. So Comet Hale-Bopp was, of course, a one-time visitor, kind of a long period Oort cloud comet. And but then the same thing has also been seen in a short period comet in the case of Tempel 1, for example. This is the normal state of that comet. It's a short period comet and not as active, of course, as Comet Hale-Bopp. So most of the active material had been blown away from the comet in previous visits. However, when the deep impact spacecraft hit the comet, then after the impact, we could see that the dust material which had settled inside so when it penetrated the surface, it ejected out all this dust with the same kind of signatures as in Hale-Bopp and the other YSO. So coming further, so there are now, of course, direct evidences, as you can see from various protoplanetary images from the ALMA, that there are gaps in the disks, again, agreeing with the scenarios for the formation of the planets, and then how the comets were thrown out from the inner regions of the protoplanetary disk. And then, so that's the motivation for trying to understand the comets. So how do we go about doing this observing? What are the things that we can do as an observational astronomer? What are the things that we can do? So typically one can do imaging, spectroscopy, and polarimetry. And at PRL, we have employed all these three modes using our observatory and of course, observations from elsewhere. And in the current talk, I will be presenting results from most of these works. So the dust that is present in the coma of the comet is shining because it is scattering the sunlight. Now the scattered sunlight is polarized, and this polarization is a function of the phase angle, the wavelength at which the observations are carried out, the refractive index of the particles involved in the scattering, and the size distribution of the particles. Thus, observing polarization at different wavelengths, which is in our control, and the phase angles, which is a geometry which is allowed by the apparition of the comet in the sky. This allows to infer the properties of the cometary dust. Okay, so how do we go about doing that? We have, for those who have not seen the Mount Abu Observatory, this is what the observatory is, and this is the instrument that we had used for most of the polarization studies until recent times. And of course, this observatory is now having a new neighbor with a bigger dome just at the back. And we'll come back to that later on, of course. And so the polarimeter has been used at various wavelengths, and we have covered a large phase curve. For example, in Comet Hale-Bopp, we were able to cover a very large range. And in fact, it showed that the Comet Hale-Bopp had the highest level of percentage polarization. as compared to any other comet. Now, this is a typical dust polarization phase curve. The phase angle here refers to the angle between the sun, the comet, and the Earth, that is the observer. And we observe it usually using narrowband filters, so-called international Halley-Foch filters in this particular case. And this is in order to avoid the contamination by molecular emission, which I will cover in the next part of the talk. So using these continuum bands, we can probe how the polarization property is changing as a function of phase and other details. Now, these once we have these observations, the next step to do is to find out how how one can infer the dust properties. Okay, so people have been considering simple ideas in the past. People started with simple Mie theory and spherical grains to try to explain the cometary dust. But recent times we have had in situ observations, and of course many other results also coming from other missions, but mostly we have looked at the Rosetta Midas and Cosima. These are two instruments of Rosetta. And following those, we decided to create this kind of a dust grain structure consisting of hierarchical aggregates, low porosity solids, and fluffy solids. I'll just show them in the picture here. These are the hierarchical aggregates, which are very porous grains. And the different color refers to two different compositions, mainly silicates and carbonaceous material. These are the solids with with moderate porosity. And then you have fluffy solids here, which are again aggregates and then solids embedded together. And these are the three ranges in porosity. And so if we look at the results from from the light scattering from this kind of ensemble of particles, then one can develop phase curves using different levels of percentage composition and percentages of the material. So in the case of, these are three different comets where we have used our model to explain the polarization for Halley, Hale-Bopp, and Hyakutake. Okay? In fact, we also show in the paper for 67P the target of the Rosetta mission. So this paper is in MNRS, and I would urge those of you interested to please go through it in more detail. Pritish has also submitted a poster on this in the ASI, and you can have a look at that as well. So the quick results are here. These are just summarizing some of the 16 pages, 16 figures in that manuscript. So we have different compositions for these four comets and different levels of morphology in terms of what kind of dust material we needed to include to get a reasonable fit in this figure, for example, for Hale-Bopp, for example. And then these are three different wavelengths, 3650 or 6840, that is in the red band, 4845, and then 3650. These three are the international Halley-Foch filter pass bands. So this has allowed us to get a good fit to most of the observed polarization. There are some constraints to be still understood on the negative polarization part, and we are looking at data which we have found in the literature, as well as some unpublished data of ours in the negative polarization side, which we will take up in the next effort. So that brings me to the conclusion for the polarization part. And the next step that we would like to discuss is the optical spectroscopy that you can do for cometary coma. The cometary spectroscopy is done using small low resolution spectrographs, and these are mounted on the 1.2 meter telescope as well as the 50 centimeter telescope. The same spectrograph can be mounted on both. And the result, the main aim is to look at the fluorescence emissions seen from the different molecules, CN, C2, C3, and others, which we can see in the in the spectrum of a comet. This is the instrument here. This is the instrument actually, and then mounted on the 50 centimeter telescope. This is Kumar observing with it, and then here he is standing next to the 1.2 meter telescope with the instrument mounted close to it. Okay. And this instrument has a slit viewing autoguider, which allows you to actually put this comet on the slit and then keep monitoring it with short exposures. So you could have like 5 to 10 seconds exposure on the comet through the guider, and then you can integrate the acquisition CCD, the comet for the comet spectrum, for half an hour to 45 minutes or longer if needed, or if possible. For example, in some comets, you don't get that much time. So typically after you have integrated for that duration, you can then get back the spectrum using your standard IRF tools, and one can then go back to analyzing all of the observed bands and features seen in the comet. So this is some of the old results, which I will not discuss here. I'll just show you examples of other results. This is the same comet Lovejoy from 2016. Comet 46P came very close to the Earth a couple of years ago, and we have a very long sequence of data on it, and Arvind is currently working on that. Hopefully we will have some results from it out very soon. And Comet 123P is a short period comet, as you can see from the name 123P. And in fact, it has very less emission, showing that it's almost depleted of its gases from the surface mostly. Comet 2016 R2 Pan-STARRS is a very special comet, one of the very few special comets where CO dominated. And most of these normal long chain spectrum was completely absent from it, but we could see in its place a lot of CO plus, and I expect we will hear a lot more about this and the formation processes going behind them in Sana's talk in the next, I think the next but one. So I look forward to that. So this would be a quite, this has been a very unique comet, and a lot of people are trying to understand what are happening in the different features here. These are all with low resolution spectroscopy. We also have carried out high resolution spectroscopy using the HESP instrument on the Hanley telescope. And we're still working on having a publication out for it. Hopefully that will be done very soon. So next, these were all comets which were comets belonging to the solar system. So comets which we knew roamed around in our neighborhood, but there have been speculations since long about interstellar comets, okay, and especially the lack of interstellar comets. So many people try to understand this by looking at the efficiency of detecting comets, and then the other possibilities like the numbers that you would expect from the numbers that would be thrown out during the chaotic formation of the solar system, of the stellar system, and so on. But most of it has been, I mean, there's a lot of literature on it. And one of the last words on this topic was by Sen and Rana, Ashok Sen and NC Rana from 1993. And they concluded after a lot of analysis that there should be at least one interstellar comet in 2 centuries of observing, okay? So this was the number based on the efficiency of detecting comets, and which basically means that if you have a larger telescope looking at the night sky, you might end up seeing a few more of these. And the other point being that the interstellar comet should be within 2 AU of the sun. Perihelion should be at least within 2 AU or close to 2 AU. So the failure to detect interstellar comets, of course, came to, the first one was detected on the 30th of August in 2019. So this was not the first interstellar object, it was the second one. That is why the name 2I. But the previous one was not a comet, it was a purely asteroidal object, although it had non-gravitational forces at work at some part of its orbit. So the perihelion of this comet was 2.006 AU on the 8th of December. It had an orbital eccentricity of 3.36, which is much, much larger than any other comet known so far. The previous interstellar object had an eccentricity of 1.2, and any other comet which have seen hyperbolic eccentricity have been mostly because of non-gravitational effects post their inner approach. Okay, and they had initially elliptical orbits to start with. So they're all solar system comets. And the other parameter which tells distinctly about this comet is that its velocity at infinity was 32 kilometers per second, which is much larger than that of the local standard of rest. Therefore, the conclusion is that it is of interstellar origin. We were able to make use of the Hanley telescope as well as the Mount Abu telescope, and results from this were published in the MNRAS recently, and we'll just discuss that in more detail shortly. So the observations were done using, as I said, both the bigger telescopes at both the locations, and we did imaging from, of course, from both the places, and spectroscopy from HCT, because it was too faint to be done from Mount Abu. At Mount Abu, we did try to get some polarization data on it, but we were not very successful due to the sky conditions. But just look at the air mass at which we had to observe in order to get this object. That's one of the challenges of cometary observations, that they are generally at very low elevations, very close to the sun at the time of observing. So amount of time available for observations is very low. Now, for this particular comet, the spectroscopy was done with about 1800 seconds of exposure, and this is the result. The inset is an RGB image from the HFOSC on the same night. This is a spectrum taken from the this is a spectrum from HFOSC, of course, after perihelion. Before perihelion, we could detect these two. We could have only minor detections of these two. They were reasonably okay, of course, but less than this one. And of course, we computed the production rates for both, and in fact with CN as a reference. And then looking at the details of how it looks, this is a plot of the production rate as reported by other observers in this plot, where the red line refers to the line of perihelion. And we had two data points on this figure, one before and just before perihelion, and one immediate, a couple of weeks after perihelion. So the point to note here is that, the data points here are all mostly from 4 meter and above class telescopes, except the last 2 points, which are from the Hanley 2 meter. All of these are taken from at least a 3.6 meter telescope. So of course, one of the reasons being that they were much fainter in the before the close approach to perihelion. So far, we haven't seen any other measurements in the literature. So what does this tell us? So basically, it tells us that CN has been stable all through almost. C2, there were just upper limits to the fluxes. And towards the end, we obtained similar fluxes as the others. But then after perihelion, there was an increase. This increase was much larger in CN and C3 as compared to C2, which tells you the same story here. This is another way of looking at it. This is the production rate of C2 by CN as a standard ratio. In the case of solar system comets, a value of 0.66 is used as a cutoff to talk about carbon chain depleted comets. So objects with values less than 0.66 are considered as carbon chain depleted comets in our solar system. This is based on a large body of work by Ahmed et al. 1995. Okay. And in our case, what we were able to see is that although the previous results were indicative of carbon chain depletion, they were ambiguous in the sense that they were not very clear that this was really a carbon chain depleted comet. But our two data points have added weight to the point that this is indeed a carbon chain depleted comet. In addition, we were also able to measure the scattering cross-section using the absolute magnitude of the comet. And we compare it with the previously measured values from the literature, mainly by Jewett and Liu. And using this, we find that after perihelion, there was a decrease in the activity of the comet. So some of the results from this are summarized here. There was an increase in the production rates as the comet approached perihelion, and there was an asymmetry at perihelion, perhaps due to a different previously unexposed region being sunlit. This is not impossible. For example, in the case of comet Eisen, this exposure to the sun of the other hemisphere made the comet completely blow up. So that was the reason that Eisen completely blew up.
Shashi, just to tell you that you have 5 more minutes.
Okay, yeah, this is my last slide anyway, so I'll just finish quickly. Okay, so the second thing that we find is, of course, that the C2 by Cn has a low value, which means that the comet is depleted in terms of carbon chain molecules. The optical colors of this comet are very similar to solar system comets. That is, it is redder than the solar color. The size of the nucleus we have estimated to be between the range 0.2 to 3 kilometer approximately. It's exactly 0.18 to 3.1. And our main conclusion in this point is that comet 2I Borisov was formed in a protostellar system undergoing a very inhomogeneous mixing of various volatile compounds beyond the CO ice line, okay, in its parent stellar system. This conclusion is based on the fact that there's a very less amount of CO. There's an excess CO and very less amount of long chain carbon in this. So it was actually a CO-rich comet as seen by other observers. So I'll conclude with a summary. And so this is that the minor bodies are an important relic from the time of formation of the solar system. Polarization observations in combination with modeling allow to infer the characteristics of the dust in the cometary coma. And of course, the spectroscopy is an important tool to understand this. In case of 2I Borisov, we were able to make many important conclusions, even though we had a much smaller set of telescopes as compared to those used internationally. This clearly demonstrates the importance and suitability of small class telescopes of the 2-meter class for understanding the minor bodies of the solar system. In fact, it can be extended further. Once the LSST becomes operational, there is an expectation that almost at least one interstellar comet should be discovered every decade. So follow-up observations will be critical in understanding the formation of planets and especially the formation of comets in other stellar systems. Exocomets, of course, have been discovered quite extensively all over the nearby neighborhood, wherever ALMA has looked, ALMA and other observatories. I'll just conclude with this slide, which is a fantastic photograph of comet Neowise from July-August 2020, where Mr. Angchuk from the Hanle Observatory managed to get this composite view. It has a spectacular ion tail and a very evident dust tail. And he tells me that the dust tail was very, very easily visible in the skies at Hanle. And to give you an idea of how bright this object was, we needed only 3 minutes to get this extremely high signal to noise ratio of this spectrum of this comet. There's a lot of detail in this, and we are working on it to come up with a publication. Hopefully, we'll discuss it at a later ASI. So with that, I'll come to the end. Thanks.
Thank you, Shashi. That was a very nice work, and you've also shown the prospects in future. So it looks very exciting.
Thank you.
So any questions? I don't see anything in the chat box.
Shyama, I have a couple of questions.
Yeah,
Can I-
sure. Please go ahead. Yeah.
Nice talk, Shashi.
Thanks.
The first question is that in one of your very early slides, you had this plot of percentage polarization and the angle, I think.
Right.
Yeah. You had two
This
sets
one?
of data points there.
This one.
That's right, open and
Yeah.
filled.
Okay. So in this, yeah, I should have explained that actually the black dots are all for comet Hale-Bopp.
Okay.
And the other data points are for other comets which were observed at other times. Comet Halley and many others.
Many
I have
others, okay.
separated them out.
Okay.
Just wanted to show that comet Hale-Bopp was a completely different comet in terms of polarization properties.
Okay, yeah, thanks. The second question was the last slide where you showed the spectrum of comet Neowise.
Yes.
That's from the nucleus, is it? The nuclear
Yes.
region?
Yeah.
Okay. Thank you.
That's from the nucleus. It was just H-phos put on the photocenter.
Yeah.
So
Thank
not exactly nucleus, but the photocenter, coma.
Yeah. So Sri Kumar, please.
Yeah. Shashi, thank you. Nice talk. Quick question on your dust size, grain size distribution. Is that a product of your analysis?
The grain size distribution, yeah, it's a power law we are finding, and then the power law values were listed actually in the analysis.
Couldn't really catch it.
Yeah, it's this number here.
Oh, the number.
Yeah.
What it could be a nominal error on that index?
That's a difficult question to answer because
the
it all depends on how much you would want to play with these numbers here.
True, but can you consider these to be really different size distributions?
I think so, yeah.
Okay.
Because otherwise they would not fit.
Models require that to be so.
Yeah.
Oh, thank you.
Okay, welcome.
Yeah, I don't see any questions. So thank you.
Thanks.
Vishal, can you please start sharing your slides? So,
Sure.
yeah, next is a talk from Vishal Goyal. It's on the effects of size of sinking iron blobs on lunar core formation. So Vishal, please.
Good evening, everyone. Myself, Vishal Goyal. I am doing my doctoral research with Professor Sandeep Sahajpal at Punjab University, Chandigarh. We do theoretical modeling for formation, thermal evolution, and metal silicate segregation of planetary bodies. Based on our lunar evolutionary models, here I will discuss the effects of size of sinking iron globes on early lunar core formation. Here I outline this talk. First, I will describe the basic aspects involved in modeling of a growing planetary body. Then I will briefly discuss the curious case of the moon. After that, I will discuss the features of our novel lunar evolutionary models, and then finally we'll discuss the results and conclusions of this study. Modeling of a growing planetary body involves integrating details of several physicochemical processes. For example, thermal processes include accretional heating, radiogenic heating, gravitational heating, solar irradiation, thermal conduction, thermal convection, thermal advection, melting, crystallization, etc. And mechanical processes include metal silicate segregation, etc. Interdependence of quantities and parameters and integration of asymmetrical processes complicates and non-linearize the numerical scheme. Now coming to the curious case of the moon. Moon is very unique among terrestrial planetary bodies. It has just 1.5% metallic mass fraction, whereas Earth has approximately 32%. This has made the core of the moon very little, that is just 330 kilometers in radius. On the other hand, it has remarkable isotopic similarities with Earth. It has also got thermally processed and differentiated into core mantle crust structure. Despite the small core, it has an early history of dynamo and magnetic field that is suggesting an early core formation. Because of distinct metallic mass fraction, The cogenetic model that suggests the co-formation of Earth and Moon in same part of protoplanetary disk seems unfeasible. Similarly, the capture model that suggests the formation of Moon and Earth at different positions and late capture of the Moon in Earth's orbit is not plausible because of highly similar isotopic ratios. These, along with other several observations, contraindicate all lunar formation models except giant impact model. In giant impact models, it is believed that a Mars-sized body impacted on protoid, which formed a debris disk. The debris disk later produced moonlets. These moonlets finally accreted on each other to form our moon. This event happened 30 to 100 million years after the formation of solar system and devoid the moon from short-lived radionuclides. That is a major heat source in large-scale melting of other terrestrial planets. Also, the formation of the moon from the debris disk was a quick event and the moon formed within initial 200 years. In 2018, we ran our models on several parameters and concluded that lunar core cannot form unless the initial temperature of the accreting moonlets is more than 1600 Kelvin. However, those models had several assumptions and limitations. In order to overcome those assumptions and limitations, we have extensively redeveloped our numerical models after that publication and have made significant advancements. I have written a novel code in Python to circumvent several limitations of earlier codes. Methodological advancements includes thermal convection was incorporated using local Rayleigh number and code was made capable of handling multiple convection zones simultaneously. Gravitational heating is also incorporated with both radial and temporal dependence. Stokes flow now has spatial and temporal dependence in comparison to constant velocity used in 2018 models. This particular advancement is responsible for the feasibility of the present study. Spatial derivatives of thermal conductivity are now not neglected. This, along with the local Rayleigh number, have highly non-linearized our numerical scheme. Optical heat transfer through liquid silicates is also incorporated. We have updated bulk silicate composition from modified H-chondritic to album to have improved material properties. Dependencies of several physical quantities on several parameters are now incorporated. We have completely done away an ad hoc assumption related to thermal relaxation used in 2018 models. Based on these advanced models, we present our preliminary results. The plots here show variation in the extent of early lunar core formation due to size of iron globes at 5 distinct initial temperatures. Here, y-axis show distance from the center and x-axis show the metallic mass fraction in that particular grid. The panels represent distinct initial temperatures in the range of 1700 to 2100 Kelvin. And colors represent distinct iron globe diameters in range of 1 millimeter to 1 meter. These plots show that the size of iron globes can significantly enhance early lunar core formation. This effect is more easily visible in different pictorial representation of the same data. Here, colors represent metallic mass fraction, whereas the quadrants of the circle represent iron globe sizes. Let's discuss the influence at their distinct initial temperatures individually. This panel presents the case of initial temperature of 1700 Kelvin for accreting moonlets. See the top right quadrant, this one. In this, we have assumed millimeter-sized iron globes. We can see that no core forms in this case. However, regions of heterogeneous density forms with 500 km of outer that is devoid of metallic iron, central 800 km part that is having primitive iron fraction, and enhanced density in between. Now look for the top left quadrant. Here we assume centimeter-sized iron globes. Here also no core forms. However, a metallic shell have formed here at 750 km. Also, the primitive part has shrunk. Now come to the bottom left quadrant. Here we assume the sub-meter sized or say 10 centimeter sized iron globes. For sub-meter sized iron globes, a little core has formed. For sub-meter sized iron globes, uh, one second. Yeah. In bottom right quadrant, core size almost doubles in radius for meter-sized iron globes. Coming to next panel, this panel represents the case of initial accreting temperature of 1800 Kelvin for accreting moonlets. In the top right quadrant, where we have assumed millimeter-sized iron globes, we can see that no core forms for them. However, the regions of heterogeneous density forms with 600 kilometer of outer that is devoid of metallic iron and central 600 kilometer part that is with primitive iron fraction and enhanced density along with a thin metallic shell between them.
Vishal, do wrap up in the next 5 minutes.
Yeah, I will. Yeah. Also for the centimeter sized iron globes in this top left quadrant, we can see that no core formed here. However, the metallic shell is thickened and moved inward to 450 km, and primitive part has also shrunk. For sub-meter sized iron globes in bottom left quadrant, we can see that a little core has formed along with a thin metallic shell, and metallic shell has moved inwards to 350 km. And remarkably, no part has been left with the primitive iron fraction. Whereas for meter-sized iron globes in bottom right quadrant, core size has grown along with the thinning of metallic shell. Coming to the case of 1900 Kelvin for initial temperature of accreting moonlets, here we see in top right quadrant that no core has formed. However, regions of heterogeneous density forms like earlier with 800 km of outer that is devoid of metallic iron. A central 250 km part with primitive iron fraction and enhanced density between them. Remarkably, a thick metallic shell also forms at upper boundary of primitive part. There is an incomplete core formation for centimeter-sized iron globes in top left quadrant. The total core size should be 330 km for complete formation, and it is below the 250 km here. In bottom quadrants, region around the incomplete core is more enriched with iron for submeter and meter-sized iron globes comparative to millimeter and centimeter-sized iron globe cases. Next, the case is of 2000 Kelvin for initial temperature of accreting moonlets. An incomplete core forms for almost every size of iron globes considered in this study. However, the bottom quadrants show that regions around core is more enriched with iron comparative to millimeter and centimeter sized iron globes. Then the case of 2100 Kelvin for initial temperature of accreting moonlets is less relevant for the aspect analyzed in this study. Because an almost complete core forms for every size of iron globes, it is nearly 330 km now. However, the extent of completeness increases with the size of iron globes. Summarizing the talk, we have explored the influence of size of iron globes on the extent of early lunar core formation. We found the influence to be positively correlated. Higher the globe size, more advanced is core formation. We found the influence to be significant. However, it may dominate only at large sizes and critical initial temperatures. Only in such conditions, it may lead to significant core formation. Further study is needed as in reality, the globe size varies spatially as well as temporally due to several factors like the merging of the iron globes and the fragmentation of iron globes due to insufficient viscosity of underlying material. Thank you.
Yeah, thank you, Vishal, for finishing in time. So there is a question in the chat box. Shyama, would you like to unmute?
Yeah, thank you. Just have a quick question on whether this Python-based code is it really a time-dependent core evolution model, or is it you just initial temperature and for that you ask what is the final core size?
Yeah, it is giving us a time-dependent core formation model. However, I have in this result increased or it is not.
Sorry, I couldn't hear that.
But yeah, it is just the result with the time dependent. I can take the snapshots at any time.
Okay, I see. Well, can I ask you a quick second question? You talked about a convective zone, thermal convection in the early phase of it. What is the approximate time scale that you are considering for such a convective zone's existence?
The formation of convection zone or the ceasing of convection zone after the cooling. What is the question?
Yeah. No, at some point, the convection zone ceased to exist, right? At what
Yeah.
age? At what time scale would that have been?
Yeah. From our preliminary results, we have found that it happens within the range of 10,000 to 20,000 years.
Okay. Thank you.
However, we have not considered the tidal heating that may increase this time period if the moon is captured into a resonance, evacuation resonance with the sun. Then it can increase this time of cooling by convection.
Thank you.
Vishal, I had a question. What would be an observational signature for this that we can, compare it with?
Actually, the direct observational signature of this would have been eroded by this time, because I have considered only early core formation. Our core is capable only up to millions of years until the solids can flow. After that, core will form by one method or another. However, one signature can be found. The moon has signatures for early magnetic field and early dynamo existing. For the formation of dynamo and magnetic field, we need some sort of currents in the core. There may be due to thermal convection, they may be due to chemical convection, or the combination of both. For those to exist, the core should be formed hot. So unless it has formed early, we cannot raise the temperature of core in case of the moon, because the giant impact event had happened after the extinction of short-lived radionuclides. So they cannot reach the interior.
Okay, thank you. We'll move on. I just want to remind the audience that you can also post the questions in the Slack channel. Can you please unshare so that Sana can share her slides? So the next talk is on modeling the atmosphere of comets with different volatile compositions. So over to you, Sana.
Yes, are my slides visible?
Yes.
Okay, good afternoon. I'm Sana and I'm pursuing my PhD at PRL under Dr. Kingshuk Acharya. So thanks to Shashi sir for his excellent talk. So he spoke about the observations of the gas phase cometary coma, and I am going to be talking about the modeling part of the gas phase cometary coma. So since sir already introduced about comets, I'm going to skip this slide. So uh, briefly, I'm going to talk about the coma composition. So the nucleus, it has a size of a few kilometers, but the coma that is formed by the sublimation of the volatile species from the nucleus, it can extend up to even up to 1,000,000 kilometers. And the volatile composition of the coma shows general diversity, but mostly it is seen that in most comets, H2O is the primary constituent. It forms almost 70 to 80% of the coma, and this is followed by CO and CO2 in terms of abundance, and trace amounts of other species such as methane, ammonia, CH3OH, and so on are also observed. Now, even though H2 is the primary constituent, it's in some comets, it has been observed that the CO by H2 ratios are much greater than 1. So Shashi sir already spoke about the interstellar comet and C2016 R2. All of these volatiles, that is H2O, CO, and CO2, they are sublimating directly from the nucleus. So we call them the parent volatile species. And these sublimated parent volatiles, they are going to undergo photolytic reactions because of the solar UV radiation, and it results in the formation of many ions and radicals, which are highly reactive, and so this drives the chemical activity in the coma. And this chemical activity occurs in the collisional coma. In the collisional coma, the mean free path is less, so that collisions can occur and chemical reactions can occur. And normally it extends up to about 10 to the power 5 kilometer. So in my work on coma modeling, I want to see that if we change the percentages of the primary parent volatiles, that is, if we change the percentages of H2O and CO, CO2, then how the physics and the chemistry in the coma is going to get altered. Um, in order to do this coma modeling, we assume a cometary nucleus that is made up of some primary ices, and these ices will sublimate, create secondary species, and all of these species will react with one another and drive the coma chemistry. And all of these species will also expand radially outward. So the density in the collisional coma, it is quite high, and because of this, we can approximate that the gas flows as a fluid, and we can use the fluid conservation equations in order to model the coma. Also, we use a multi-fluid approach where the ions, the electrons, and the neutrals, they are treated as separate fluids. Now, the reason for adopting a multi-fluid approach is because when chemical reactions are going to occur, the energy that is released, it is non-uniformly distributed amongst the different species. Say, for example, in photochemical reactions, the photoelectrons being lighter, they are going to carry away a majority of the energy. So depending on the mass of the reactants and depending upon the type of the reactions, there is non-uniform distribution of energy. So we use a multi-fluid approach. And these model equations, they are basically the form of differential equations, and we can perform a numerical integration of the equations, and with that we can get quantities such as the number densities of the different species, the temperature, and the velocity profiles of the coma. So in my model, I have considered a total of 213 species that are connected by over 2,500 reactions. And the cross sections for all these reactions are taken from the feed rates in the KITA databases. So coming to the equations for the model, so these are the four equations, respectively, equations for the conservation of number density, mass, momentum, and energy. So in these equations, R is the cometocentric distance, that is the distance outwards from the nucleus. N is the number density of any particular species. So since there are 213 species, we will have 213 such reactions. V is the velocity. We assume a common velocity for all the three fluids. T is the temperature. So three different fluids will have each will have their own individual temperatures. And we have the right-hand side other source terms, which I'm going to talk about in the next slides. So this term, this net energy source term, it can be written in terms of G, which is the net thermal energy source term. So coming to the source terms, so first of all is the number density source term. Now, if we take any particular chemical species, now it is going to get created by one set of reactions and it is going to get destroyed by another set of reactions. So the sum total of the rates of all these different chemical reactions, it will determine that how much of that particular species is present at a particular distance. So this and also this source term will also depend upon the number densities of the reacting species. The total mass and momentum terms, when we sum over all the three fluids, that is the ion, electron, neutral fluids, the total mass and momentum terms get conserved. And coming to the thermal energy source terms, so uh, for each of the three fluids, we have three different thermal energy source terms. And this has several components. So first of all is the component coming due to chemical reactions. That is how much energy the fluid is going to gain due to exothermic reactions. Apart from that, there is also exchange of energy between the between different fluids. So this term it like when electron and neutral species, they can undergo elastic scattering. So this term describes the exchange of energy in case of elastic scattering. And in case of inelastic scattering, there's also exchange of energy because the neutral species, particularly H2O, they have vibrational and rotational levels. So because of inelastic scattering, the neutrals can get excited to the higher vibration and rotational levels. So there is exchange of energy because of that also. There is some amount of radiative cooling in the neutrals, and there is also Coulomb interaction between the electronic and the ionic fluids. So we have all these source terms in place, and we have a differential equations. So we can, by some algebraic manipulation, we can recast the differential equations that I showed previously. We can recast them as first order equations in temperature, number density, and velocity, and then we can integrate them for a set of initial conditions. So the initial conditions that I have used, I have considered two different cases. Case A corresponds to the volatile composition of comet Hyakutake. So in this case, H2O is the dominant parent volatile, and the abundances of all the other volatiles are given with respect to H2O. So we have 20% of CO with respect to H2O, CO2 is 6%, and so on. And case B is the representative composition for the comet C 2016 R2. Here, CO is the dominant volatile, CO2 is about 18%, and here there is very little water, only about 0.3%. There are also a lot of trace elements that are present, trace species that are present, and their abundance percentages are given in this table. So after performing the numerical integration for these set of initial conditions, we get some results. So I'm going to explain some of my results in upcoming slides. So first of all, this is the temperature profile. Now on the left-hand side is for case A, where H2 is the dominant volatile, and right-hand side is case B, where CO is the dominant volatile. Now N, E, and I, they correspond respectively to the neutral, electronic, and ionic fluids. So in case A, we see that up to about 100 kilometers, the electronic and the neutral fluid temperatures, they are very closely coupled. Now, the reason that this is happening is because there's a lot of H2O present here, and H2 is a highly polar molecule, and uh, it has a very high inelastic scattering cross section. So all of the electrons that are created, they quickly transfer their energy to H2O due to collisions. And also in here, the densities are also very high, so the collision rate is also higher. Now, as we
Sana,
move
5 more minutes.
yes, I just have a couple more slides. Yeah, so as we move outwards, the density falls off, and hence the collision frequency decreases. So the electron temperature rises because it transfers lesser of its energy to the neutral fluid. Now, if we see case B, here there is no coupling between the electron and the neutral temperature, and the reason for this is because CO has an inelastic collision cross section, which is almost 3 orders less than that of H2O. Hence, we do not see any coupling. Here, I have shown the number density profiles of some of the parent volatiles. So most of the parent volatiles, they follow roughly as 1 by r square, except for ammonia. The reason being that ammonia has a very high photodissociation rate, so it gets photodissociated very fast in the outer region. In the inner region, since there is extinction of UV, so photodissociation rates are slightly lesser. And here I have shown the number densities of some of the ionic species that are created in the coma. So we will see that. So I'm going to take each species one by one. So first of all, we see CO plus. Now we see this CO plus abundance is almost 2 orders of magnitude higher in case B, because there's a lot of CO, and photoionization of CO will produce a lot of CO plus. CO2 plus is also more abundant because CO2 plus is produced by charge exchange of CO2 and CO plus. So here we have 6% CO2. Here we have 18% CO2. That is why we have more of CO2 plus here. Again, here there is very high abundance of HCO plus because CO reacts with many of the ionic species to produce HCO plus. Also, bigger ions are more abundant in the case of the CO-dominated coma. And the reason for this is, first, if we consider CH4 plus, so CH4 plus is created by charge exchange of methane with CO plus and CO2 plus. So more amount of CO plus and CO2 plus will naturally result in more amount of CH4 plus. And CH4 plus again reacts with CH3OH to form these other bigger ions. And finally, we see that here there's a lot of H2O. In case B, H2O is very less. In spite of that, in the innermost regions, we see that H2O plus has similar abundances in both the cases. And the reason being that we have very high CO2 plus abundance here, which is going to react with H2O to form H2O plus. Similarly, for H3O plus, H2O and HCO plus will react to produce comparable abundance of H3O plus in both cases. So to conclude, we see that whichever is the dominant parent volatile, if it is H2O or if it is CO, that is really going to drive the physical and the chemical conditions of the coma, because we saw that the temperature profiles in both the cases are quite different, and also the ionic composition is affected when we change the relative abundances of the parent volatiles. Thank you.
Yeah, thank you, Sana. Are there any questions? Yeah, Sri Kumar.
Quick question to see slightly outside the topic that you've been discussing, but is there any evidence of phosphorus? More interestingly, I asked the question of phosphine. Is there any trace of phosphine? Is there what is an infrared window where we could actually detect this?
Okay, so far a lot of volatile species have been detected in coma, but as far as I'm aware, there has been no detection of phosphine as such.
Thank you.
Okay. So I think there are no more questions here. So please post in the Slack channel if you have. So let's move on to the next talk. Ritesh, can you please share your screen? Ritesh will talk about the evidence of multiple episodes of superflares during the birth of our sun. Ritesh, over to you. Hello, Ritesh, we can't hear you. Hello.
Hi, Shyama.
Yeah.
Actually, I'm currently at a place where the signal is probably going to be erratic.
Okay.
So I've uploaded a video which is going to pay out.
All right.
I'll stand by should there be some problem. Yeah.
Sure, yeah.
Okay.
Thank you.
So can you hear this?
Ritesh, we cannot hear you. So I was wondering whether it's a recording where the audio is also recorded, or are you going to speak?
So I had recorded it and I could hear my voice over there at that time. So I don't know whether
Okay, I couldn't. Does anybody else hear the video?
Just let me just share it
if
again.
that doesn't work out, I'm going to start now. So it should be
Yeah, I
fine.
think that is better.
So there is option when you share the screen. There is option called checkbox called shared sound. So if you click that share sound, so sound gets shared on the screen share.
Okay. So Abhirup, maybe it's better that you share it and then Ritesh can speak.
Yes, just a second.
So let me try and do it from here itself. That should be fine. I mean, if it stops in between, then probably we can shift back again to that.
Okay.
Does that look nice?
Yeah. Okay.
Give me 2 seconds.
Okay. Vishal says in the chat box that YouTube audio cannot be played from a browser.
No, we have played it yesterday. Just a second.
Was it okay? Do you want to give the introduction, Ritesh?
So basically, our solar system constitutes of a star which is primarily very, very ordinary, but it has but our planetary system is very special in the sense that so far as we know, life exists only on Earth amongst all the stellar systems that we have studied, meaning by the interaction of solar energetic particles with the gas and dust present in the solar gas and dust present at that time. And because the CI is a very ordinary form G2V about star, 0.5 million years later than the canonical time, fiducial time of formation of the solar system, we inferred that the intensity of irradiation at this later stage of time was pretty high, and this work was published in the Nature Astronomy. However, since the CI had formed about 0.5 million years later, we could only infer possibilities of existence of multiple episodes of formation.
Ritesh, we've lost it.
Okay, so maybe what I'll do is I'll share my screen and we should go ahead with that without wasting further time. Okay, so let me just do it this way. So good afternoon, everyone. I apologize for all the difficulties. I just wanted to make it safe for everyone to be able to hear to this talk, and therefore I preloaded it on the YouTube. But yeah, technologies don't always help us. So in this talk, basically, what I'm going to say is that our solar system is very, very special in the sense that so far as we know today, Earth is the only planet where life exists. And therefore, in that sense, our solar system is very, very special, although our sun is a very ordinary star. So the grand architecture of our solar system established very early in its life, in first 10 millions or so, and that primarily sets out all the conditions for all the planet and planetary bodies that would continue to evolve for the remaining, let's say, about 10 billion years. So the initial 10 million years would determine the evolution of all the planets and planetary bodies for next 10 billion years or so. So therefore, it is very, very critical to understand what kind of cataclysmic events were happening in the initial 2 to 5 million years. That will set out the conditions for evolution of life, evolution of all other planets, and importantly, the question of evolution of life on different planets. So there are several first order questions that are currently being investigated. One of the key questions is to understand the evolutionary and dynamics of the nascent sun, and to determine how, with what frequency, for what duration of time, and with what maximum solar intensity was the sun doing at its nascent stage. So how active magnetically and geodynamic and dynamically the sun was in its initial stage. This will probably determine the way solids would evolve when they would aggregate, get irradiated, the kind of material that would have, and all those conditions would be determined by the condition of sun at that time. So the key question that we are going to answer today is, did our sun, like several of the stars that we have seen in our near neighborhood galaxy, did our sun go through the same kind of stages? Although it is expected, but it is important to know the exact time periods of these events, because an event happening 1 million years later or an event happening 1 million years earlier would very significantly change the number of solids present and the distribution of matter that exists in the protoplanetary disk. So an exact time of these events and at what time for what duration these happened is very critical to understand the evolution of protoplanetary disk for the next million years and billion years for the formation of planets. So a major advance in this area was made when we could, for the first time, show the presence of a very short-lived nuclide, 7 beryllium. 7 beryllium is the short-lived nuclide with the shortest half-life of just 53 days. So it allows you to study events processes at an yearly time scale. So 7 beryllium decays to 7 lithium, as shown in this slide, in just 53 days. So in a CI from Efremovka meteorite, we could, for the first time, establish confirmed presence of 7 beryllium at the level of 1.2 times 10 to the power minus 3. Because the half-life is so small, it is not possible to synthesize this nuclide outside the solar system and bring it inside and get it incorporated into first forming solar system solid, which itself takes a few 10,000 to a million year time scale to form. Therefore, we could conclusively establish that this nuclide should have been produced locally by the irradiation of gas and dust present in the solar system at that particular time. And but the time of formation of the CI is about 0.5 million years after the fiducial time, which we consider as the time of the formation of the solar system. So this CI had formed 0.5 million years later. Therefore, it could only tell about the time of its formation, which is, so at its time of formation, 0.5 million after the formation of solar system, this CI probably suffered an irradiation event at this level to be able to produce 7 beryllium by 10 beryllium at this level. So the question that remained open is whether there were events earlier than that, and if there, what kind of intensity, frequency, and duration they were happening at that time. So typically, how do we do it? We do it by studying what is called as short-lived radionuclides, which are present in meteorites. These short-lived nuclides decay into their daughter nuclides in their respective half-life. For example, 41 calcium decays to 41 potassium in a half-life of 0.1 million years. And currently, it is inferred to be at the level of 4.5 times 10 to the power minus 9. So the two nuclides that we are going to discuss in this particular talk is 10 beryllium, which decays to 10 boron with half-life of 1.4 million years, and the other extremely other very important nuclide, 7 beryllium, which has got half-life of just 53 days. Remember, the others are in million years, while the half-life of 7 beryllium is just 53 days. So now these radionuclides are produced by different sources, and therefore you can use these new radionuclides to trace out from what source these radionuclides came from, and therefore you can tell about the cosmochemical processes that took place at that time to have made these radionuclides present in those solids. So as you can see, 7 beryllium and 10 beryllium for a long time was believed to be just produced by radiation, and therefore they were used as the traces for radiation. But recently it has been shown that 7 beryllium, 10 beryllium could also be produced by supernova. So that initial argument, so the long-standing argument that 7 beryllium and 10 beryllium were produced only by radiation was the basis for that was taken away. So we have to show it specifically that these nuclides are produced only by radiation and supernova to be able to make that claim. So this is a typical, so supposingly 7 beryllium was incorporated in an early solar system solid, then it would decay with its characteristic half-life. So if you measure 7 beryllium today, it would be equal to 7 beryllium that was present initially, plus the additional 7 lithium coming from the decay of 7 beryllium. So this can be converted into a linear equation of this type, whereby you can measure 7 lithium by 6 lithium today and 9 beryllium by 7 lithium in a particular object. If you plot these two, 7 lithium by 6 lithium versus 9 beryllium by 6 lithium, you'll get a straight line, which the slope of that line will give you the initial abundance of 7 beryllium by 9 beryllium, while the intercept will tell you what was the composition at the time of what was the lithium composition at the time of formation of that particular object, or at the time when the isotopic closure took place. Typically, these excesses are very small, and therefore they are usually expressed in per mil, which is the difference or deviation from the reference value in parts per thousand. The same can be said about 10 beryllium. The 10 beryllium decays to 10 boron in half-life of 1.39 million years. So to be able to show that records of early solar system at the time of the formation of the solar system, or at time t equals to 0 rather than 0.5 million years, we took a CI which we had studied previously amongst. So we had to select a specific CI which had very pristine characteristics, which had formed very early and had all the properties that could help us elucidate or could help us trace out the evidence of 7 or 10 beryllium. So a CI from Vigrano, which had been previously studied using high precision aluminum magnesium dating to have an age of 7.5 times 10 to power minus 4. So this CI had formed at time 70,000 years after the formation of the solar system.
Ritesh, 5 more minutes.
So yeah, I'll skip most of these things, and that should be. So we had to figure out whether there is characteristics in all those. So we had to do a detailed study of its composition, abundance, variance, and minerals, and all that. So the important thing to remember over here, by doing a detailed study, we could find out that this CI should have formed at 1420 degrees Celsius. It should have cooled at about 0.5 degrees per degrees Celsius per hour, which is very important, as you will see, because lithium and beryllium boron tend to diffuse very fast, and therefore it is very difficult to find the records of lithium isotope because it tends to diffuse very fast. So in this CI, we did lithium beryllium boron studies, and from lithium beryllium boron studies, we could find out for the 7 beryllium decaying to 7 lithium, we could find out a value which is 4.3 times 10 to power minus 3, which is about 4 or 5 times higher than the one that we had previously studied. So you can see there are some very well spots with very well resolved excesses. So in the melilite in the melilite in the CI, we could find a range of values for 9 beryllium by 6 beryllium, and some of those. One important thing to state over here is that that the lithium isotope, when the meteorite is in the outer space, the lithium is produced also cosmogenically, which tends to obliterate, or which tends to get added to the previous to the original record of 7 lithium by 6 lithium. So we have to correct for cosmogenic correction that the parent body has seen, and then be able to get to this record. This is very critical, because you can have changes in the value at the level of 300, 400 per mil when the excesses are only so small. So similarly, for that same CI, we also did 10 beryllium, and from 10 beryllium boron studies, we got a value of 1.4 times 10 to power minus 2, which is about 100 times higher than what we had seen. So once we have these two nuclides, we could make calculations to show that if we take a solar composition and the spectra of particles is 2, then we can simultaneously produce 10 beryllium and 7 beryllium in a time period of about 2 years. is the color all visible or no? Okay, so I'll go ahead. So, so, uh, so what we so now we have CIs which have for which we have which we have different 7 beryllium by 9 beryllium ratios, because these 7 beryllium would decay in a one year's time. So typically these objects tend to record the irradiation history at that particular time. So previously we had a CI which had found at 0.45 or at about 0.5 million years. Now we have a CI which had found at at time t equals to 0.07 million years after the formation of solar system. Then for a few CIs, previously studies had been done, but they had not done cosmogenic correction. And so they were saying that the object did not have a, we did a cosmogenic correction to find out that some of those objects which have been previously reported in literature, if we do a systematic correction to those, then we could also see that they also showed varying level of 7 beryllium by 9 beryllium, typically lower than what we have seen in this particular study. Similarly, the same can be similarly for these objects. 10 beryllium by 9 beryllium existed previously, and therefore that has also been plotted with the two objects that we had studied. So now from this you can see that the abundance tends to vary with time, and the error bars are different. So because these 7 beryllium has got half-life of 1 million years, although the error bar coming from the 26 aluminum by 27 aluminum that we have taken to be the fiducial marker of the time at which these objects were forming. Now you can see that there is a variation in the intensity of irradiation that these objects have seen, and they tend to vary over a period of time.
Ritesh, I think the 15 minutes are over.
So I think I will stop at that time. I've said most of the things that so I will acknowledge my
Thank you.
advisors and mentors. Okay. And with that, if somebody has a question, I'm happy to answer it.
Yeah. Thank you. Are there any quick questions? We are a little bit running out of time. So otherwise, please write on the Slack channel. I think Ritesh will be available to answer. So shall we then move on to the next talk, the last talk in this session by Biswajit Mondal at PRL. Biswajit will talk about the soft X-ray spectroscopy from the using data from the X-ray solar monitor on the Chandrayaan-2 orbiter. Biswajit, can you please start sharing your screen?
Yeah.
Yeah, go ahead.
Okay. Hello everyone. I am Biswajit Mondal, and today I will talk about the soft X-ray spectroscopy of white solar corona with XSM. So first I will briefly introduce you what is XSM. So XSM is a soft X-ray spectrometer which observes the sun from the lunar orbit and provides the soft X-ray spectrum at every second. So XSM operates in the energy range of 1 to 15 keV for up to M5 level of solar activity, and above M5 level of activity, the lower energy cutoff increased to 2 keV by bringing a beryllium filter in front of the detector by a filter wheel mechanism. So this is the image of the XSM detector package, and it uses the silicon drip detector, and its resolution is 175 EV at 5.9 keV. The unique design of XSM makes it possible to observe the dynamic range of sun from sub-A to X9 class, and its field of view is 40 degree. So now why soft X-ray spectroscopy is important? So this plot shows the dynamic spectrum coming from an ionized plasma from UV to hard X-ray regime, and this red curve shows the spectrum for 2 million Kelvin plasma, and blue curve shows the spectrum for 20 million Kelvin plasma, and this green shaded duration shows the energy range over which XSM operates. So you can see that in the soft X-ray regime there are lots of these emission lines along with the continuum are present. So this spectrum provides us the temperature and ion coverage which are not available in UV or hard X-ray regime. So if we model the spectrum in this energy range, then we can get the origin of the this emission and the condition of the plasma emitting such radiation. So now I'm coming to the point that how we model the spectrum and get back the plasma parameter from the observed spectrum. So the observed spectrum C of I, which is related with the theoretical spectrum F of E by this relation. So here again, the calculation of F of E requires some atomic database, and for that purpose, we uses the Chianti atomic database. So if we convert this theoretical spectrum with the instrument response R, which is known from the instrument calibration, we can get back the theoretical spectrum C of I. So we know the observed spectrum C of I from observation, we know the R, but we are interested in this theoretical spectrum. From this equation, the calculation of this f of e is not possible by directly inversing this equation. So the general technique is the forward fitting of this observed spectrum by using a chi-square minimization algorithm. And for that purpose, we uses the XPack, which is X-ray fitting package, which is widely used in X-ray astronomy. But at present, there are no model within XPack is available for the calculation of this theoretical spectrum from the Chianti database. So for that purpose, we developed a XPack local model for the calculation of the uh, 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 theoretical spectrum for a ionized plasma from Chianti database. And this is the flowchart of the technique we employed. And this is the interface of our model within XPack. So you can see that all the elements from helium to zinc are included along with the temperature and emission measure. So any of these parameters can be considered as a fitting parameter in our model. And this is a comparison plot between the spectrum calculated by our model and the direct Chianti calculation. Here, yellow color dash shows the direct calculation from Chianti, and different color shows the calculated spectrum by our model. So our model calculation is very well matched with the direct Chianti calculation. Thus, the high resolution broadband spectra of XSM makes it possible to distinguish the elemental line complex of magnesium, aluminum, silicon, etc. And hence, from the spectral fitting, we can estimate the temperature of the plasma along with the elemental abundances of these elements. Thus, one of the science goal of XSM is to measure the temperature along with the elemental abundances of the solar corona. So, uh, so the elemental abundance problem is one of the long-standing problem. So in this plot, in the y-axis, this is the ratio of the elemental abundances in the corona to the photosphere of the elements, and x-axis shows the fast ionization potential of the elements. So you can see that all the elements whose fast ionization potential is less than 10 eV are higher in abundant in the corona than their photospheric values. But for high FIP element, the coronal elemental abundances are nearly same to their photospheric values. So this is a well-known observed phenomena, but why it is happening is one of the unsolved problem in astrophysics. So the current understanding of this problem is based on the ponderomotive force model. So ponderomotive force is a nonlinear force which acts only on the ions at the top of the chromospheric layer, where the temperature is high enough to ionize these low FIP elements. And once they ionize, they influenced by this force and go up to the corona and increase their abundance in the corona. So theoretically, it is found that this ponderomotive force is strongly depends on the magnetic field activity and the temperature of the plasma. So with XSM, we measured the absolute abundances of the elements for the quiet corona, where the magnetic field activity is much weak compared to the active corona. So this is the XSM observation of the minimum period of solar cycle 24. So here in the bottom right corner, this plot shows the y-axis, the number of sunspotless days, and x-axis shows the time. So you can see that in the minimum of solar cycle 24, having the year 2019, have the largest number of sunspotless days, which indicates that this minimum was the deepest minima in last century. So it is a great opportunity to observe the quiet sun during this period of this period of the sun. So only there. So in this period, XSM is well observed the sun, and these are the XSM observation during this period and used in this study. So this period span from September to November 2019 and February to May 2020. So here blue curve shows the XSM observed flux, and during this period we also looked into the UV and X-ray images and found that there are some durations such as marked by this blue color where no active regions are present in the solar disk defined by NOAA, and this orange color shows the durations when active regions are present on the solar disk. So you can see that the presence of the active region increases the observed solar flux by XSM. Also, we have found some durations such as this pink duration where the XSM observed the excess emission, but no active regions are defined by NOAA. So in this study, we define these blue shaded durations when no active regions are present as a quiet duration, and we use the data of these durations. So this is the same plot as shown my previous slide, and these are the representative uh, uh, full disk images observed by UV, observed by AIA and XRT telescope. AIA is for UV and XRT for X-ray images, and you can see that the presence of the active region in this orange shaded durations and also in the pink shaded durations, some major activity are present on the solar disk. But in the quiet period, no activity, no major active regions are present on the full disk images. Also from these X-ray images, we found that during this period, the most of the X-ray emission coming from these hot points, these are called X-ray bright points. So also in this quiet duration, we XSM observed large number of microflares, which are outside active regions, and for the present study, we exclude the duration of this microflare as well. And the details of this microflare study, please visit the poster presented by Mithun. So we have generated all the spectrum for this quiet period and fitted the spectrum for all of these quiet durations. So these are the two representative fitted spectra for two quiet period days. And after fitting, we have estimated the temperature and the elemental abundance of magnesium, aluminum, and silicon. And this gray color shows the non-solar background spectrum. So we have total 76 such quiet days, and we have fitted all the quiet days spectrum, and this is our final result. So here panel A and B shows the variation of the temperature and emission measured, while panel C to E represent the variation of elemental abundances.
Biswajit, 5 more minutes.
Yeah. So here this red, green, and blue points represented the result for the spectra integrated over 1 day, multiple day, and full quiet period. And our estimated temperature lies in the range of 2 to 2.1 million Kelvin, which is lesser than the active region temperature, which is around 3 million Kelvin, but slightly higher than the diffuse corona, which is around 1 million Kelvin. So this also verifies that we are basically observing the X-ray bright points. Also, our emission measure estimation is around 14 into 10 to the power 46 per centimeter cube. And from panel C to E, here the color dashed line shows the reported coronal values by several authors, and this green band shows the range of photospheric values reported by earlier authors, and this is our measurement. So you can see that our measurement lies in between the photospheric and coronal values, specifically for magnesium and silicon. So this is a very interesting result because as we are most of the we are observing the X-ray bright points, and it is well known that the magnetic activity of these X-ray bright points are very weak compared to the active corona. So according to the present understanding of conservative force model, their abundances should be in between the photospheric and coronal values. So to the best of our knowledge, this is the first time observation of measurement of the elemental abundances of X-ray bright points, and our results are well agreed with the present understanding of theoretical understanding of FIP problem. So before I stop, I would like to introduce the another interesting result we found from XSM observation. So during this solar cycle 24 minima, XSM also observed large number of small flares. So for the evolution of these flares, we have studied the time resolved spectra of these flares. So we have studied the flares within the active region, and this is the representative result for one flare. So here this gray color represents the flare light curve, and this black point represents the evolution of the parameters. So the panel A shows the evolution of temperature, panel B shows the evolution of emission measure, and panel C to F represent the evolution of elemental abundances. So here for the elemental abundance evolution, we found a very interesting result. So you can see that in the pre-flare durations, the elemental abundances are nearly coronal value, but during the flare, this elemental abundance coming down to their photospheric values. And again, in the decay phase of the flare, these are going back to the coronal values. So this is interesting because for the small flare, this is the indication of that during the flare, this plasma materials is coming from deep interior of the chromosphere to the corona. So the details of this result will be we will discuss in sometime that somewhere else or maybe in the next time. So thank you.
Yeah, thank you, Biswajit. Are there any questions? Yes, Ritesh.
Biswajit, thank you. I'm surprised that you don't seem to quote a recent paper that came out from India itself on this time evolution of abundance with flares. You aware of that paper?
Yeah, I aware about that. So here we are just showing that representative thing.
No, I agree, but it's always nice to recognize other work that happens in the country as well. Thank you.
Yes, sir. Yes. Okay. Thank you.
Yeah, so if no more questions, thank you everyone. So this is the end of the session. And I guess the Slack channel will be alive so that you can have more discussion in that. Thank you. It was a nice session. 4 slightly different topics. I think we all enjoyed it. Thank you.